So back to our example from before, where we deleted points based on the distance to the surface of an object. And we've seen that this can create some unexpected things because we forgot that the inside of an object has also a distance to the surface. And just to finish this problem first, there's actually another way of solving this, which doesn't work for complex shapes, but for a sphere at least it will work. What we did here, we read out the closest position on the surface of this NURBS sphere, on this primitive sphere. Then we calculated a distance to that. And when the distance is smaller than 0.5 meters, then remove the point. We chose to find the closest point on the surface. And this is what the min-pos is doing. Technically, for this case, we could have found a good solution by just saying, all right, since this is a primitive and only has one point in the center, we could have said, just read out the position of the only point that exists. And this would actually solve this as long as we increase the distance. Let's actually put this on a parameter. And if we find a good number, then this is a bit of a different logic actually. It's not looking for the surface, it looks for the center and then deletes everything in a certain distance. This actually is a solution for this. But that's not always possible, especially again when you have complex objects. For example, if I replace this with a toy, then this will not work anymore. Somewhere there is 0.0. Yeah, it has 12,000 points somewhere here. Yeah, it's not really working for a case like that, you know, if you want to have something more following the shape. So what can you do here? I talked about this before. This is where SDFs come in. And since we understand what SDFs are doing, and that is saving the distance to the surface, this is actually kind of already built in. So all we have to do really is we turn our toy here into an SDF. And here is a little optimization thought. I could do this afterwards, of course. But then whenever I move this object, and I can feel it a little bit, and I think you can see it, it's a little bit, you know, there is some calculation happening in the background, because whenever I move it around, I have to rebuild the SDF. In this case, changing the order so that I create the SDF first and then move the result around, then you can see it's much, much faster because it doesn't have to be rebuilt. You know, just a small thing. Things like that can optimize your calculation time quite a bit. So, and now I have an SDF here, and this is the volume that is created. It's called surface. I personally, it's totally up to you, I change this usually to SDF, so it's quick to type, and also then quick to type in here. And the thing is to read out a volume, and this seems like it's only important for when you work with actual volumes, so like Pyro or stuff like that. But as we can see, SDFs are very useful for even stuff outside of visible volumes. So what we need to know is that there is a volume sample function that reads out from a volume. And it's actually surprisingly simple, even though it looks here a bit more complicated, but it's again the input, which is the second one, because that's where our SDF is coming from. Then the volume name, which we just called SDF, and then a position, which of course is the position of my current point, because I want to know what the SDF is relative to my current point. So let's do this. Now, of course, just to remind ourselves, what we're doing right now is we're running not over the volume, we're running over every single point of the grid. And relative to that point, we read out the SDF. So we want to write this into an SDF attribute, and we want to volume sample from the second input. The name of the volume is called SDF. Let's double check. That's the name of the volume. And then from what position? Of course, from the position of the current point. And that's it. And when we look here at the SDF number, it's 0.3 and then nothing else. And the reason is that my SDF is up here and my grid is down there. So it never reaches really the bounding box of it. And that means it takes the last data that it finds. So keep that in mind. And I think we talked about this. The distance outside of the surface that is actually calculated, I can define in the VDB from polygons, because that's the exterior bend voxels. So if I increase that, you can see that my box gets bigger because more voxels are calculated outside that are filled with a distance. Now let's actually see if that already, yeah, and this already changed something, because now some points, as you can see here, I think, some points are now already inside of the VDB and can read out the number, and all the others get the furthest that's inside. This is why most of them have 1, but some of them have something that is smaller than 1. So what can we do with this? Of course, we can now use this directly. We can use this like a distance and say, okay, if the SDF is smaller than, let's do again 0.5, or actually it's 0.3 or something, then remove the point. And this then looks like this. Maybe we can do it with a merge. That should work so that we can see both. Yeah, that works. And now you can see that since the SDF holds the distance information, the deletion will be much closer to the actual shape, of course, because it's based on the shape. And that also means when we look inside that if I make my toy even bigger, that you will always have... No, actually, that's something you shouldn't do. Let me correct myself. You should actually not scale a volume, or more specifically an SDF, because the numbers in there then will not be scaled with it. So this, while this works, and it's actually interesting that you can do it, it's not very accurate because the distance, of course, is then wrong. So I would rather actually scale my toy before I create the VDB, like this, and then it's more accurate actually. So what I actually wanted to show you is that the inside is of course also deleted, because why? We know why, because the distance inside will be negative and therefore definitely lower than 0.3. Everything inside will be lower than 0 actually, and this is, you know, the magic of SDFs. We understand now even more why SDFs are so helpful and such a powerful tool. So this can be, you know, depending on your case, an alternative to the distance function. Of course, it's a bit more work because you need to turn something into a VDB first. But as you can see, it can be really helpful depending on what you want to do with this. Okay, now I don't want to make this video too long, but as a quick example, what you could use this for as well is when later on we work with Pyro and you have smoke and you have something like this here, like a, you know, a medieval oven, or a cooking place or whatever, and you have smoke, and smoke is as usual called density, then you could use that to darken the environment based on contact with the smoke. So what I could do is a point wrangle, and the first input is the geometry and the second input is the smoke. And then I, first of all, to make sure this works, I can set the color of the oven to white, and then I will darken depending on the smoke. So I could, for example, check, okay, is there smoke where I am currently? So I check from the second input the density volume relative to my position for each point. And if this is higher than 0, so if there is smoke, then let's quickly check this. I just set my color to red, for example. And this then looks like this. So in general, it works. But you can see, you know, it's everywhere the same. So it doesn't take the strength of the volume itself into account. So what I would instead do is I take my color, which was set to white, to 1, and I just subtract whatever smoke I find. So if I don't find any smoke, nothing will happen. But if I find smoke, the color will be darker. So if I run this, you can see it looks much more reasonable. And if I run this, you can see now that this is actually what I wanted, that the points are darkened. Of course, now I have the problem that this is, you know, doesn't have memory, so it happens every frame independently. So I just put the whole thing into a solver and then connect everything. And then I just make sure that this will accumulate. So I put my point wrangle here so that the second input is the second here as well. And if I now look at the result, what I should see now is that the darkening is accumulating. It's way too strong now because it accumulates every frame. So let's quickly adjust for that by just lowering the effect a little bit, maybe to 1/100th of this. And also, of course, what will happen at some point is the color will get negative. So if the color is smaller than 0, let's make sure we put a limiter in so that the color will never be lower than 0. And then so never darker than black. So if I run this now, you can see this should work much better. Now it's too little. So let's increase that to 0.1 maybe. Let's try it again. Yeah, that looks better. And here you can see it's a really cool effect because it really darkens the environment very naturally, but now it's too strong again. So maybe something like 004, I have no idea. If I waited long enough, it looks like this. So at the very least, maybe if the fire is off or something, it will end up like this. So either way, it's an interesting, idea that the smoke is sampled and then the environment reacts to that. Maybe you can try this yourself as a little homework. Another small note that is important to mention is sometimes you don't want to read out a scalar volume, so a normal fog or an SDF, but sometimes you want to read out a velocity field. So for this, I created a velocity field that looks like this. So just, some vortex with a little bit of curl noise on top. And I want to align my tubes here, which are just copied on the grid. And for that, I want to set my normals according to this velocity field. So of course, what I can do is I create a point wrangle and connect my velocity field with that, and could say, okay, please set my normals to the volume I read out from the second input. And this is of course vel. So as you can see, this works with normal volumes and with VDBs. And you would actually expect that the normals are now, aligned to this velocity field here. But they're not. When you look at the normals here, they're all set to 0. And this is a really tricky problem when you don't know about it, because the volume sample can only read out float values. As soon as you try to read out velocity fields or vector fields, then you have to add a little v at the end for volume sample vector. And now you can see that this actually worked and our normals are read out correctly. And don't be surprised, our velocity field actually only was in this area. So if I increase the area a bit more, you can see that it actually reads out the correct directions. And this is how you read out vector fields. So it's basically the same logic, but you have to add a little v at the end, and it's very easy to overlook this as a beginner. So I hope this is helpful. Thanks very much and see you later. Cheers.